Hello everyone, my name is Reviraj Sonar and today we are going through Verilog. It is a hardware description language and this video is a comprehensive guide to the Verilog. So introduction to Verilog. Verilog is a powerful hardware description language, HDL, used for modeling electronic systems. So this presentation will guide you through its features, syntax and applications. Whether you are a beginner or mastering or looking to enhance your skills, mastering Verilog will enable you to design and simulate complex digital circuits effectively. So Verilog is similar to the VHDL. If you have studied VHDL, it is very easy for you to understand and implement or write the code of Verilog. So of both languages are same, but it is different. So we have said so much about hardware description language, but we don't know what is hardware description language. So hardware description language is essential for simulating design and simulating digital circuits. It allows engineer to describe the structure and behavior of electronic systems. Verilog or along with VHDL is among the most widely used HDLs, providing a way to model hardware at various abstraction levels. So as I said, hardware description language is essential for designing and simulating digital circuits. So before we implement it, before we implement the hardware of any the digital circuit, we have to simulate in software so that we can reduce the cost of it, or if we have any error in our code or anything, so we can pinpoint it from the simulation by because of these languages. So hardware description language is majorly used for simulating and designing of the digital circuits. So now the basic syntax of Verilog. So understanding the basic syntax of Verilog is essential for writing efficient code. In Verilog, modules are used to organize and encapsulate functionality. Key component includes assignments for defining combinational logic, always blocks for sequential condition and operations, or conditional operations, and initial blocks for setting up simulations. A good grasp of these elements makes it easier to write, debug, and manage Verilog code effectively. So the basic syntax includes modules. As we see in if you have studied VHDL, you have know that the functionality of our whole code we write it in an architecture. So the same thing goes here in Verilog. The functionality of our whole code, also the ports of our whole code, we write it in a module. So it only we only wraps our whole code in the module. So next is assignments, which are we use in combination logics. The basic assignment we have given by assignment component. Always blocks, which we use for sequential or conditional operations. Initial block for setting up simulations. Next is Verilog or data types. So Verilog supports various data types that helps define signals and variables. Common types include wire, register, and integer, each serving specific purpose. So first is wire. Wire represents combination logic and connects different modules or components. So wire, it is a represent combinational logic. It connects different modules with modules and different components with other components. Register, it is maximally used in sequential logic because it stores the value. As we know, in sequential circuits or in sequential modelings, we have to store some values. So because of this, we use the register in that in sequential logic. Integer, it is general purpose variable, especially that we use in loops or counters or test benches. Understanding these data types is essential for effective hardware modeling and writing accurate Verilog code. So there are different types of modeling in Verilog. So Verilog offers several modeling styles to describe hardware at different abstraction levels. So first is behavioral modeling. Use always blocks to define functionality, ideal for high level simulation. So with the use of behavioral modeling, we can make the high level simulations or high level digital circuits with the use of behavioral modeling. Next is data flow modeling. This describes combination logic, which are very basic, and using control assignment assign. Next is structural modeling, represent hardware by connecting model instances similar to schematics. So first is data flow modeling in Verilog. Data flow modeling in Verilog, it is made of many things. This is first is container assignments. We use assign for input and output relationships. Then signal types. we typically employs wire for outputs in data flow modeling, combination logic suitable for circuits with output dependent only on circuit inputs, only on current inputs. So the circuit operator uses logical and arithmetic operator for clarity. Modularity supports hierarchical design for reusability. Immediate evaluation, the output of our code is evaluated immediately in data flow modeling. And simulation, this is application for both testing and hardware and implementation. So here is an example of half adder with data flow modeling. So as I said earlier, we encapsulate our whole code in module. So here it is module and it module name. Then by parenthesis we are giving the ports. So A is input, B is input, output is sum, and output is carry. So after closing the ports parenthesis, we are assigning the values which is sum, which is as we know, so in full adder sum is a XOR b. So here this operator is represented as XOR. In VHDL, as we know, we have to just write XOR between the variables, but in here in Verilog we have to give the symbolic representations. So same for the carry. As we know, carry is A and B. We are going to assign carry as equal to A and B, and we are ending the module. Here is a simple code for half adder using data flow modeling. Here we are only assigning inputs and outputs. So here we are doing the test bench of the half adder. We have half adder code we have written previously. So as I said earlier, we write the whole code in the module. So here is the module, and the module name we have given it test bench, and we are using register because we have to store the values of A and B. Then we are using wire for sum and carry because we are connecting the input and output. Then we are going to instantiate the half adder. Okay, so here we are going to instantiate means we are going just like the port mapping we have done in the VHDL, VHDL. So here we are also doing that. So we are assigning the value A to the A, B to the B, and sum to the sum, and carry to the carry. And it's just a port. We are connecting the ports of the half adder we have written previously and now of this code. So next is initial begin. We are going to begin with the test bench. So for the A, if A is equal to 0 and B is equal to 0, then the hash 10 means it is the delay of 10. So it is just comment by double slashing we are commenting it. And for if we have to display something, we can use this operator and display. And same for this. And here we are ending the test bench, and lastly we are ending the module. Simulation and testing. Simulation is a critical step in Verilog design process. It is not only critical in Verilog, it is critical in VSGL also, or any if we are going to design any electrical system. Simulation testing, it is very critical processes in the process. So it actually allows you to verify the behavior of a hardware before implementation. Actually, before we implement our circuit in hardware, we have to check our circuit is right or wrong by our circuit of our behavior of the circuit is right or wrong. We can check it by using simulation and testing. For simulation testing, the tools we use like ModelSim, Vivado, it facilitates the testing and enabling you to catch errors early and ensure design meets specifications you have need. So in conclusion, mastering Verilog opens doors to advanced digital design and simulation. By understanding its syntax, data types, and constructs, you can effectively model complex systems using Verilog. Continue your learning by exploring practical projects and advanced topics to deepen your expertise in hardware description languages. Thank you.